All right, so we have f, our original function, and our first and second derivatives, and we want to use those to describe the shape of our graphs. So what we need to know is we need to know where the first and second derivatives are positive, where they equal 0, and then of course we need to figure out what that tells us. So first of all, let's talk about the first derivative. When does the first derivative equal 0? When will that function equal 0?
When x is equal to 6.
No, that's going to give us an undefined value. That gives us a 0 in the denominator, Garrett. We want a 0 in the numerator. So
when x is equal to 4.
When x is equal to 4. Now, the value you pointed out is just as important because we have critical numbers not only when the derivative is equal to 0, but when there is no derivative, or when the derivative is undefined. So f prime of x does not exist, I should say, when Garrett said one was when x equals 6. What's the other value where it doesn't exist? What else will give us a 0 in the denominator? 0. Excuse me. Because 0 to the 1/3 there is also 0. So that's also going to make our denominator undefined. Okay. So we have some critical points, which tells us that's probably, or that could be where we have a local maximum or local minimum. Let's look at our second derivative. And then what we'll look at is the intervals where they're each positive and negative. So our second derivative, where does that equal 0?
Be 6 and 0 as well, right?
That's not where it equals 0. That's where it doesn't exist. That's when our denominator is 0. So still important points. But will that second derivative actually ever equal 0? Taylor kind of shook her head. Why not, Taylor?
I don't know. I know that they don't exist.
Okay.
6 and 0.
What needs to happen in order for that fraction to equal 0? Think about how we got this. What was that?
The numerator would have to equal 0, and there's no way that we can manipulate the numerator.
Exactly. Exactly. The numerator would have to equal 0, and when it's just -8, there's no way to get it to be equal to 0. So that's not going to happen. All right? So what we want to look at now is what's happening in between those. So we've got some critical points, 0, 4, and 6. So let's set up our intervals. I'm going to write... Well, actually, I really like how the book does it. I'm going to use kind of a number line approach, but I'm going to break it down in a table like the book does. I'm going to run out of room, though. Let's just add a little bit to this. So our critical points, as we said, are at 6, 4, and 0. So that gives us 4 basic intervals. Now the book sets up a table, and I think this is a really nice way to do it. So the first interval is when x is less than 0. Then we have between 0 and 4, between 4 and 6, and greater than 6. And what they do is they look at just at the first derivative for a second, and they look at how that applies to f overall. And the way they break it down is really neat. It's kind of what I've always done algebraically, but they're making a table out of it. They're going to look at the main terms of f of x. Or sorry, of f prime of x. So in f prime of x, you have 4 minus x is one main term. You have x to the 4/3, and you have 6 minus x to the 2/3. And so what they say is if x is less than 0, what does that tell us about 4 minus x? Is it positive or negative? If x is less than 0, is 4 minus x positive or negative? Positive. Okay. Now I wrote the wrong thing in this box here. This should be a 1/3 power, not a 4/3 power. I looked at the second derivative instead of the first. So if x is negative, is x to the 1/3 positive or negative? Remember that 1/3 power is a cube root. So if you take the cube root of a negative number, what do you get? A negative number. What about 6 minus x to the 2/3? Now, the easiest way to look at this is to say it's 6 minus x, the cube root of that, I guess, squared. And so no matter what 6 minus x is, and no matter what its cube root is, you're squaring it. So do you get a positive or a negative result? A positive result. So what we have is we have 3 basic terms in our first derivative. And for this interval, one of them is positive, one is negative, the third is positive. So what's the overall sign of f prime on that interval? If you got a positive over a negative times a positive, what does that give you? It gives you a negative. Exactly. You've got a positive number divided by a negative number times a positive number. We don't care what the value is. We just care about its sign, because that's going to tell us whether it's increasing or decreasing. So on that interval, f prime is negative. So f is decreasing on that interval. And so they go through this with every interval. So I'm gonna go through it a little bit faster. We're going to say if we go for values between 0 and 4, 4 minus x is still positive. X to the 1/3 would be positive because we're taking the cube root of a positive number. And this is positive. And just a spoiler alert, this one's always going to be positive because of this right here. You're squaring whatever your value is. All right, so f prime of x is going to be positive there, which means f is increasing. Next interval between 4 and 6, we're doing 4 minus a number bigger than 4. We're going to get a negative for both of those intervals. But we're doing cube roots of the positive numbers, so when we do cube roots of positive numbers, we get positive numbers. So those are both positive. And so our results for both of those sections are negative, which means the function is decreasing here. So this tells us the intervals where our function is decreasing. Now, what also is helpful is to know what the second derivative is doing in those areas. So when we evaluate it with the second derivative, that will tell us whether or not we have local maximums or local minimums. You can intuit some of those from the first derivative and say that we had a critical value at 4, 6, and 0. Now at 4, since it's increasing and then decreasing after 4, it's increasing up to 4 and decreasing after 4, that tells us that's a local maximum. At 0, it's decreasing before and increasing afterwards. That tells us that is a local minimum. But it's important to note that our derivative doesn't exist there, so it's not a smooth minimum. It's actually a bullet nose curve. It's a little point, like an arrow. And then at 6, it's decreasing and then decreasing again. So we don't actually have a minimum or maximum there. We have an inflection point. Okay, so 6 is an inflection point, not a local maximum or minimum. That's where the graph changes concavity, but doesn't actually turn around. So if we were to draw this using that information, we're just going to do a quick sketch. We don't have to get super detailed. Let me pull up a quick graph here. Now, what I might want to know, since I have my local max and local minimum there, it might be helpful to know what my values are. Okay, if I put in 4 to the function and 6 to the function and 0 to the function, so if I plug them into here and see what I get, I'll find that I get 4 and 2 to the 5/3. You could get a decimal answer; it'd be just as fun, just as acceptable. If I put in 0, I get 0. If I put in 6, I get 0. So I know exactly where my local max and local min are, and I know what my where my inflection point is. So I've got a point 0, 0. That's a local min. I've got 4 and 2 to the 5/3, which is a little more than 3 if I calculate it out. That's my local max. Oops, but sorry, I put that at 5, not at 4. And then I've got 6, 0 as an inflection point. Now, going back to the table, up to x equals 0, I have to be decreasing. So that means my graph has to be decreasing. And if I evaluate the second derivative, I'll see that it's concave down there. Okay, so it should look more like this rather than like this. The other thing that tells me that it doesn't look like this is if I use this curve and continue that pattern, okay, then this is actually not only a local min, but my derivative is defined there. Which I know is not true because we said that our first derivative is undefined at x equals 0. So that tells me that I can't have this kind of shape. I have to have more of a vertical tangent so that it looks like this. Okay? Because my derivative is undefined there. So I can't have a nice smooth curve. It's got to come to that point. All right, then we're increasing between 0 and 4, and we hit that maximum at 4. Between 4 and 6, we're decreasing, and we're concave down. Okay? Now, I know it's concave down because if it was concave up, it would look more like this, and I'd have another problem with my derivative at 4. But my derivative was defined to be 0 at 4. So it's going to be that nice smooth curve. We're going to hit our inflection point there, and an inflection point is where we change concavity so it starts to be concave up. Okay? So we have a graph that looks essentially like this. Okay? This shouldn't be, there we go. Essentially like this. That's the level of detail that we need. It doesn't have to be really any more precise than that. We have to have kind of our concavity nailed, our local max and min, and our inflection points. And that's really the limit of what we need to reach. So what we're going to do when we come back, we're going to break here. I recorded the graph here and this construction, so I'll post that on Blackboard for those that missed. And when we come back, we're going to work on doing the same process with the next example in the lesson, and then we'll move on to 4.5. So we'll end early for break and for lack of students, and you guys enjoy your vacation.